I would like to share you some work that we've been doing in the context of creating fair applications, in the context of, at the end, making sure to integrate at very large scale clinical and genomics sequencing data. And that slide represents, is maybe the most important slide because it represents what we are working on, where we have, and it comes from the report from the National Academy of Science in 2011 on taxonomy of precision medicine, building a knowledge network for biomedical research, where they took the analogy of Google Map. We all have on our iPhones today, we use Google Map with all the different layers of information, satellite codes, traffic jams in real time, the transportation, and that enable us, centered by GPS coordinate, to have all those different layers of information being made available. What we have been working on and now succeeded to create is information commons, where we put together all the different layers of information per patient, clinical data, genomic data, retrospective data, prospective data, clinical trials, EHR, longitudinal data, any kind of clinical genomic data has been integrated within this system that enables to scale. As you'll see, we have more than 250,000 full genomes linked to all the clinical data in one project. And this really enables us to create this information common that enables to go from one layer to another to be able to make new biomedical discoveries. And the whole context related to this is to, because all the data that we are producing right now is so big and so wide that it cannot be processed within our on-prem infrastructure. And so we all have generating lots of data, genomic, clinical, imaging data. We all have our analytic pipeline. And what we've been working towards within my team is how to leverage extremely secured cloud environment where the data is hosted in the cloud, but where we push the analytics next to the data to be able to scale in the different compute activities that we want to do, but also in the context of sharing. Because when another investigator has some data that he wants to make next to the initial data or have its own analytic, avoiding sending hard drives, how to leverage the cloud to enable to create this very, very secured environment. And so just by the numbers on one of the project, BioData Catalyst, where we have 3.4 petabytes of data with 250,000 participants, 160 full genomes that have been integrated, all the clinical data next to all the genomic data. And that's all the top med clinical studies, where there's more than 80 studies, Framingham Heart Study, Women's Health Initiative, and everything has been put in the same database model in PI-SURE, the open source Apache 2 license project that we created, where we integrated all the clinical data next to all the sequencing data. So in PI-SURE, we load the annotated VCF next to all the clinical data to be able to make those correlation across all those different data types. And this model, we've been using it across many different funded projects, including the Diagnostics Network, also being used internally at Quest Diagnosis, the Boston Children's Hospital Biobank, where there's 2.9 million patients, the JAC network across 5 institutions, where we have more than today 5.4 million patients using this infrastructure, where there's all the clinical and the genomic data, and many other projects. And the overall of the infrastructure that we created is to store all the clinical and that can be EHR, longitudinal data, registries, clinical trial, and any kind of sequencing data, all exome, all genome, into the PI-SURE high performance data store that can be Apache 2 license, open source, that can be queried with the PI-SURE API, either from a search portal where there's Boolean queries where you can add the different elements, clinical and or genomic data from any element, any variant in the annotated VCF can be queried in real time, but also from an analytic portal to actually do the science, to where there's an R and Python connector that enables to access the picture API. So and that's where we developed, and I'll talk about it, a new platform, open source service workbench on AWS. But you can also use existing platforms like Terra, like 7Bridges, or many other existing platforms to actually connect and access to the picture API to analyze your data. So the idea is really to have the search portal to get a first sense without writing a line of code of feasibility, how many patients, how to create this data set, narrow it down based on your research question, narrowing down the number of patients, narrowing down the number of variables, and then actually doing the work in a workspace environment. And that's why we propose this open source tool, Service Workbench on AWS. How does it look like the user interface from picture, where that's showing you from the BioData Catalyst, where you can query based on any clinical variable, for example, here, the sex, next to any genomic information, for example, here, having a variant in the gene CHD8, and then I can add additional elements based on the annotations on using, and we use the VIP annotation model to annotate all those variants. So based on the severity, based on the gene ontology, or many other variant annotations, to then narrow down your cohort. And there's, for example, here, 533 participants. Then I can export the data into a statistically ready file. Or for the genomic data, I have a pop-up window that will show you the variant in the Variant Explorer, the VCF that has been narrowed down to only the population of interest, and being able to see the allele frequency and comparing with also Nomad, to be able to explore and see if you're interested to go further in exploring this potential variant. So that's based on the user interface access, but there's also the API access to actually be able to do the work. And we're providing many examples using picture with the example of, in this GitHub repo, of access data using picture across all our projects, the same GitHub repo, the same code, so they can be copy and paste based on other examples from other projects. And this can be run on any platform, computing workspace environment, to be able to analyze the data, where there's the full clinical data and the full genomic data, annotated VCF that can be accessed and explored in R and Python to be able to get started. We also provide a data access dashboard based on your credential from, for example, the BioData Catalyst, to know what you are allowed to use, to be able to, based on the clinical and genomic data, based on the authorization process from DBGAP, of what you are allowed to use based on your current authorization or the authorization of your PI that he gave you access to. So it enables you to have a simple access point, and there's all the links at the end of the presentation, for you to see today, based on your DBGAP authorization, which dataset you can use today within Picture BioData Catalyst based on the your current authorization. So I've showed you different screenshots based on the search portal. Now on the service workbench on AWS, where we didn't find an open source workspace environment that existed, where there's many different proprietary tools or tools that are being deployed at only one institution. So what we did is to look at the best feature from many of those platforms, because we needed to have it for security compliance inside our own Amazon account and not to use it as a service. And so this is why with AWS engineers, we worked and developed Service Workbench on AWS, which at the beginning was just a pilot project 2 years ago in my lab, where we wanted to democratize the access to public cloud computing, of having a very nice user interface for investigators to be able, or students, to access to workspace environment at scale, but without having to access the AWS console, without knowing how to code and create the infrastructure for the AWS, but they were just interested in having RStudio or SageMaker, creating the notebook in R or Python, but not interested in all the infrastructure part before. And so that's what is being managed by this Apache 2 license project And this for the purpose of teaching, but also research, with full building control and with full security of the data. And so on the drawing board 2 years ago, I wanted to have something that worked across multiple funded research projects, multiple teaching courses, across multiple AWS accounts. And doing the billing across accounts is difficult. And so that's something where it's much easier with Azure and Google, where the billing is outside the account, where with Amazon, the billing is inside the account. So with AWS engineers, we worked on creating this. And at the end, but having something centrally managed, secured, that can meet HIPAA compliance, that's the case, meeting very soon high trust compliance and also FISMA compliance, working towards that, into a very nice user interface. And this was one of also the very strong requirement that I had to work on this with Amazon, was it had to be on an Apache 2 license. At first, the Amazon lawyers wasn't very keen with that. They wanted to use their specific Amazon Web Service license. I was against, because it wasn't great for not having no IP issues across all the academic projects. And it took 1 year of a nice and kind battle, but at the end, they accepted. And this is the very first Apache 2 solution from AWS, fully supported, and that's the key. This is a project of AWS. It is not anymore a project from my lab. It is not in my GitHub repo anymore. It is an official AWS solution. It's maintained by AWS. There's more than 8 full-time developers from AWS working on this, maintaining it, and making it available to the world. And so that's awesome, because I don't have to maintain it anymore. They maintain it, and they do a much better job than we could do internally. And this can be used in medicine, but can be used in many other domains, that anything that is related to research on making the access to workspace and creating environment at scale. So how does it look like? There's CloudFormation templates that enables you to launch any kind of workspace environment that you're interested in. It could be a simple virtual machine, an EC2. It could be a SageMaker notebook to be able to have Python, R, everything already pre-installed, all the SageMaker, all the TensorFlow machine learning, deep learning tools from Amazon, using the best of the state-of-the-art to get started. RStudio, using the latest version to be able to run directly and launching an RStudio environment for you, for your student, for your research project. Or at very large scale, an EMR, Elastic MapReduce cluster, that, for example, enable you to launch HAL, the HAL variant store created by Benjamin Neal at the Bird Institute, can be launched and installed in one click from Service Workbench on AWS. And for all those environments, you choose the scale. You choose, because after selecting which workspace environments, you can select what the size of it, and everything is configurable based on the number of CPUs, GPUs, and who's authorized. A student is not authorized to have access to the GPUs unless authorized for a specific course, but you can choose the scale of it. And then what's great, this is an open source project accepting open source contribution to have your own workspace with your own tools that you want. For example, we're working to have IGV being also deployed as one workspace to enable with one click to have IGV being deployed and linked with all the S3 bucket, because one of the key components also is the function of having the link with the Amazon S3 bucket to store the data that is already mounted in your workspace environment to read with read and write access. So yes, there's many proprietary tools that exist, but this is the very first truly native open source product maintained by a cloud vendor to enable you to launch workspace environment at scale. And so this project, Service Workbench, we use it across many of our projects, and including the GIC network, where the analytic portal that enables to make the link between the data, clinical and genomic data from all those pediatric institutions, where we have the discovery portal using picture, as I showed you, and the analytic portal. At first, when we wrote the grant and got funded 3 years ago, we were using Jupyter Hub. Jupyter Hub is great, but not scalable in the context of based on the size of the data, based on the size of those environments. So I didn't want to maintain the installation of Jupyter Hub. Having it as a service with service Workbench on AWS creates something totally scalable with all the security compliance, because we have the accounts, Amazon account from all the different institutions. So the data stays behind the firewall of each institution in the context of and enabling real true distributed learning. And that's how we have now 5.4 million patients within this network. And I'll just end by the latest project that we were awarded participating with many other institutions. So it's not just a lab, but there's where we are very grateful to be working for the Office of the Director from the NIH on the MHEAD program, Artificial Intelligence Machine Learning Consortium to Advance Health Equity and Research Diversity, where it's a massive program of $100 million over 2 years that enable to make all those tools available for many different communities. And that's why we the two tools that I provided, that I showed you, Picture and Service Workbench, will definitely be part of the program with many other tools, but that really enable to advance and to I think enables infrastructure equity, because anyone with a simple laptop with okay internet connection can have access to all the power of all those tools, because everything is running in the cloud at scale. And so this definitely enables to create infrastructure equity across the research environment. So this was a very quick overview of the things that we are doing within our lab. So I don't know if you have any questions.
Paul, wonderful. Thank you so much for this talk. The one question I was going to ask you is just really around how you solve this kind of fundamental problem of making sure that a software initiative which started as a research project gets a sustainable life. And the way you've done it is essentially through offboarding it or kind of finding a maintainer in the shape of AWS. So could you just tell us a bit more about how did you manage to make it happen? Because so many science labs actually really struggle with the software maintainability piece. And this is perhaps one of the best solutions I've heard so far. How did you do it?
So everything, and I have a presentation at reInvent 2 years last year, I recorded, where I shared the story of exactly how this happened. So this started exactly now 3 years ago at reInvent in Las Vegas, where I was going from one booth to another at the Amazon conference and realizing all those different services. For example, SageMaker have an option to, and they can do really great machine learning, deep learning, all that, but there's an option to have notebooks. And I was done of maintaining the Jupyter Hub environment, the notebooks and all that. So having notebooks being maintained, the installation, the upgrade by Amazon, they will do it much better than we would do. So looking at this, looking at all the various components that already existed, what we needed is an orchestration, a nice user interface on top of it with a few clicks for someone and then that knows nothing about the cloud to be able to launch out of it, to launch an environment. And so discussing with my contact, and every institution, every company has a way to contact Amazon. And it's the same with the other cloud vendors of this representative, and explaining, hey, I would like to do so and so and so, but it's too difficult to do directly by my lab. Can I get some help? They like the idea and they say, hey, there's a ProServe service from AWS. I can get 2 engineers working for you for free or
Nice.
3 or 6 months. Let's get started to do a project. And because they liked it, they really like this idea. And they said, but this could be a competitor to Terra platform from the Broad. And I said, well, yeah, I had the Terra platform in mind, but Terra platform is on Google, not Amazon, and also there's one installation of Terra, which is maintained by the
see.
board. It is not maintained, it's not, so there's a compliance issue for some of my projects where the data cannot leave Boston Children's Hospital. So I needed to have the installation behind my firewall. And so taking the best of each of those platforms, working with the Amazon engineers, they accepted to, and they funded the ProServe service. So at the end, it didn't cost me anything for this service, but it's just my time of working with them and architecturing it and making sure that, and testing it. The first version, there were bugs and all that, but then at the end, there was a first round of ProServe. Then they said, we like it. Let's go to the second one. Then, okay, let's do a second round of ProServe. And then they liked it a lot. And we did a third term of ProServe, which was getting ready for large-scale production and not to be hosted in my GitHub repo, but to be maintained by Amazon. Because they liked the product, which was a pilot project internally just for my lab at the beginning. And they liked it. And they fully agreed from the get-go. It's an open source Apache 2 license from the beginning. I do not own it. It's not mine. We are finishing writing a paper about it, and that's what works for in an academic group. But the whole purpose is the fact that it's maintained by them is so much better than maintained by an academic team because it's much more sustainable. So the direction the direction of the project, I'm not controlling it. I give feedback. I reuse it in production at the DBMI in the Department of Biomedical Informatics across multiple groups. We use it for now for the past 3 years for teaching with my course, and they help us. And definitely, and it's working great. There's many different improvements, but the key is there's no fee to use it. You only use the fee of the AWS underlying services, but the orchestration, it's an AWS solution, and which you can find here. So AWS service Workbench. You can download it directly from. Is there a chat where I can share it with everyone?
Yes, there is a chat actually. The private chat we used is not the one. Yeah, I'll just post it to all the participants.
So comments? Is it in comments?
It's in comments, yeah, indeed. If you post on comments, everybody will be able to see it.
So that's the service work, the overall nice page. But the key, and I think most of the people here would be interested in this, is the GitHub repo of where there's the AWS Service Workbench Lab to be able to deploy very easily the platform in your Amazon account. So the downside is, yes, it only works with AWS. It doesn't work with any other cloud vendor. But at least at first, I wanted to be 2 years ago. I really wanted to be cloud agnostic and having all my projects working across cloud vendors. But I stopped. I stopped because this didn't enable us to have a very high level of security compliance because it's too much work to make everything highly secured. And so then yes, we picked AWS because we had to pick one. But you can definitely do a lot of things also with Google and Azure. But with AWS, I got outstanding support to enable. And the example of this project is one of them, where they were really interested in helping us to move this forward and to enable access to this at scale. And so highly encourage everyone to test both picture on one side for the integration at scale of clinical and genomic data, but also Service Workbench on AWS for the workspace environment. And both of them are totally disconnected. You don't need to use one or the other, but it's just different tools in the toolkit of, and everything Apache 2 license, no question about this. so that there's no IP issues to be able to use across any of your projects.
I see. And when you were given this access to the engineering resource at Amazon, what were the sort of milestones that they looked at, or like how did they approach? Essentially, I must imagine they must have somehow argued that this was good for the customer base or good for the revenue in some way. How did you like, what were they looking at between the phase 1 of the project, which was like a small project, just a couple of months of FTEs, into moving into the bigger project? What was the decision-making process on the side of AWS?
It was a competitor to other existing platforms.
I see. So it was like user-based.
Something that was missing from AWS. There wasn't, and maybe I should have done this earlier, but there wasn't a live. So that's a service workbench production environment at DBMI. There wasn't a live project solution maintained. So there's many proprietary platforms that exist. So 7 Bridges Genomic, DNA Nexus, or Terra from the board that exist, but none of them are truly open source that you can install within your security boundary. None of them. And so that's something that was crucial for us to enable this. So there's, so I'm going quickly, but there's more than 145 users. And how does it look like for the user? There's 264 workspace right now within the environment. I can here create research workspace. So that's the user experience. I can choose EC2 Linux, SageMaker, 2 versions of SageMaker, RStudio, or a very large EMR cluster to deploy HEL, for example. For example, here, SageMaker Notebook. Next, I choose a name, my project, and this goes into different Amazon accounts behind the scene. There's different Amazon accounts that can be used for the billing. That's the one we use, for example, for teaching. The size of the environment. Do I want a T22 extra large, which is 32 GB of RAM, or just half of it is enough? The billing, estimated billing, and by default, it will automatically stop after 60 minutes. That was one of my very strong requirements. Yes. Where Amazon wasn't happy with this. He said, why do you want to stop it? Everyone is expensive. And the big issue with the cloud is the fact that everybody forgets about stuff. And then if your window is not open, if nothing is happening, if you have nothing running, then so they check the CPU. And if the CPU is idle for 60 minutes, it will automatically stop. And then you can restart it. It's not terminated. So the way... So, and it takes 7 minutes to generate, but in 7 minutes, you have your workspace environment with a link to be able to launch and access it, the environment. And so, for example, here, I'm accessing one from one of my postdocs, and then by Connect, I can access her SageMaker environment with now running what is running. And what's awesome, it's linked with S3 bucket. This S3 bucket has terabytes of data behind the scene. There's terabytes of data behind this S3 bucket, which is automatically linked with the workspace environment. So it resolves the issue of how do I share data, read and write access with S3. S3 is great, but I need a nice user interface in front of it. And this enables you to do this. And I can use Jupyter, or if I prefer Jupyter Lab, and we don't install it. It's maintained by Amazon. It's using the notebooks from SageMaker to be able to have your compute next to all your S3 bucket at scale. So that's so I can choose the notebook in the Condor, Python, everything, the whole power of and choosing which kernel. All those kernels are maintained by Amazon. So I don't have to waste that time. I've spent so much time maintaining this. So that's why that was the whole idea of the conception of this 3 years ago is I don't want to manage this anymore. Let's have Amazon do it, but we needed to have a nice user interface to bring all those different components together. So it was about having TensorFlow, SageMaker, Jupyter Lab, RStudio, HAL, Apache, cost, HIPAA compliant, FISMA compliant, all control of cost, and that's what Service Workbench is, putting all these different pieces together at scale.
Yeah, no, it's wonderful, and well done for fighting with AWS to essentially reduce the amount of money they would earn from researchers by introducing a circuit breaker in the shape of the 60-minute timeout. I have to admit that's one of the features actually we had to implement in Biomage ourselves.
And you can change it, but by default, the default, that was the key. The default is 60 minutes. Then if you want to take it off, you can. If you want to put it to 10 minutes, you can. But the default is 60 minutes.
Yeah, makes sense. Makes sense. Wonderful. Yeah, an amazing job and such a creative solution to solve a very, very common problem in academia of maintaining software. Paul, thank you so much for coming. It was a wonderful talk.